So we have already seen some links between these complex numbers and linear algebra ideas that we have developed so far, but there are more. Okay, for instance, we've seen that all arithmetic operations can be done on complex numbers. We can add them, and of course we can subtract them. That's not a big deal at all. We can multiply them, and we've just seen that we can divide them. Okay, so all these arithmetic operations can be done. So the idea is that we could view the complex numbers as scalars. So what we could do is develop all of linear algebra with vectors and so on, but instead of restricting ourselves to using only real numbers, we could extend everything we've done to complex numbers. Pretty much everything that we have learned so far in terms of matrices and so on remains the same. We're not going to go there, don't worry, but just keep in mind that it can be done. And in fact, this extension to complex numbers allows us a number of extensions to of properties that we've seen to a whole bunch of other situations, and also we can obtain a certain results in more generality. For instance, one of the things you may remember is that for given a square matrix, its eigenvalues, well, they are the roots of the characteristic polynomial. As such, they may be real or they may be complex. If they're real, we can work with them as long as we're working with real numbers. But if you're complex numbers, if you're imaginary numbers, then we cannot use them in the regular real number based theory of matrices and eigenvalues. But if we're assuming complex numbers as the scalars, then everything is hanky-dory, and we can use all the eigenvalues, but whether they're real or complex, we don't care, and we can do all kinds of other things. And for instance, we can do all kinds of processes like orthogonalization and so on much more easily, and to a larger variety of matrices. So it is possible to consider vector spaces that satisfy all axioms, but with complex numbers as the scalars. And again, I mean, this is another extension we can make. So just like we can talk about regular Euclidean vectors, but using complex numbers and matrices and so on, we can also extend our interest to, for instance, vector spaces of functions, which are functions of complex numbers, and all kinds of wonderful things like that. Complex eigenvalues and eigenvectors, as I said, become very, very intriguing, and we can do all kinds of things with them. And as well as we can develop all kinds of inner products which are based on complex numbers. Again, this is just for your own information, for you to know that they can be done. But as far as the topic is concerned, what we'll expect you to know is basically what a complex number is, how to add them, multiply them, and how to look at them as being isomorphic to two-dimensional regular vectors, and so on and so on. So just focus on those ones, and then you'll be fine. And then hopefully in the future you will be studying some of these links you have in front of you to a deeper extent.